So consider the function 1 over sine 1 over z. Okay, so we'll do this gradually. So we first think of what 1 over z looks like. I'll just plot it for real positive z to keep things simple. Okay, so 1 over z looks like this. Okay, it increases without limit as z goes to 0. So sine of 1 over z for positive real z looks something like this. I mean, okay, sine obviously varies between minus 1 and 1. So roughly speaking, if you've got 1 over z, this is getting smaller and smaller as you go to infinity. So it's going to do something like, where it's going to tend, as z goes to infinity, this tends to 0, and sine of 0 is 0. So it's going to tend towards 0. Then it's going to go up, and then as z gets smaller and smaller, this gets larger and larger. So the oscillation is going to get faster and faster. Okay, so they get infinitely fast as this approaches 0. Okay, so there's infinitely many zeros, which incidentally are simple zeros, of course. Infinitely many zeros as we approach z equals 0. Now what we're going to do is take 1 over that. Now obviously 1 over 0, I don't really need to draw all of this, 1 over 0 is a singular point. Okay, so that means you've got infinitely many singular points as you approach z equals 0. And what we're trying to find is an example of a singular point which is not isolated. And such a singular point is when you get is z equals 0. Because if you think about it, at z equals 0, you can't, if this is the point z equals 0, you're going to have an isolated singularity. You're going to have a singularity there, but it's not isolated, because however small you draw a disk, you'll always have infinitely many other singularities inside that disk. So an example of a non-isolated singularity is z equals 0 for this function.